All right, welcome to Physics Chapter 2, Lecture Number 1. This lecture is going to cover the On Your Own problems 2.1 through 2.6. And we're going to go with our one-dimensional motion equations. So to use the following equations, motion must be in a straight line and acceleration must be constant. So I really love this chapter. It reminds me a lot of my high school physics class and some of the things I remember from that. And we're going to learn three major motion equations. So just write these equations down. We've got to memorize them. Equation 1 is final velocity, okay? So just use v, and it's a vector, is equal to initial velocity, that's v naught, plus acceleration times time. Okay, you absolutely have to memorize that equation. So let's look at problem 2.1 on page 39. So that says a car traveling at 35 meters a second passes a police car which is moving at 23 meters a second. Policeman doesn't have a radar gun, so he immediately starts to speed up in order to match the speeder's velocity. That way he'll be able to measure how fast the speeder is moving. If the police car can accelerate at a rate of 2.5 meters per second squared, how long will it take for the policeman to match the speeder's velocity? Okay, so the way I like to do these problems is let's write out what we know and what we're trying to solve for. Okay, so we only know this one equation so far, so we know we're going to be using this equation. Well, the final velocity, because the police car wants to match the speeder's velocity, is going to be 35 meters per second. Let's write that down. The initial velocity, that's given in the problem, the police car started at 23 meters per second. Accelerations given in the problem. The acceleration of the police car is 2.5 meters per second squared. And we want to know time. So it's really just a matter of plugging into this equation. Okay, we have 35 meters per second is equal to 23 meters per second plus acceleration 2.5 meters per second squared times time. All right, let's subtract 23 from both sides. Usually I won't show this step, but that would be 12 equals 2.5 times time. So solving for time, we're going to bring the 2.5 underneath the 12. All right, and when you do 12 divided by 2.5, you'll get 4.8 seconds. All right, so pretty cool. Now, if you want to know how this equation was derived, it's in the text. Feel free to read through that, but I'm not going to require you to derive these equations on the homework or on the test. All right, let's move on to the next equation. Okay, I'm going to go ahead and leave equation 1 on the board because our last three problems we're going to be picking from all three. Equation 2 that you have to memorize is final velocity squared is equal to initial velocity squared plus 2 times acceleration times displacement. Okay, let's work a problem that involves that equation. So problem 2.2. So this is on page, flip over to page 43. Okay, it says a car has a maximum acceleration of 1.15 times 10 to the fourth miles per hour squared If it starts from rest and accelerates as quickly as possible for 500 yards, 5 times 10 squared would be 500, what will its velocity be? And then it gives you there 1,760 yards in a mile. So we're going to have to do a conversion here. So let's go ahead and convert yards to miles. We could convert miles per hour squared to miles per yard squared, but that's really not a very common unit. So we're going to take 500 yards, put it over 1, and we want to convert that to miles. So put miles on top, yards on bottom. The 1 goes by the bigger one. There's 1,760 yards in a mile. All right, so that's 0.284 miles. All right, so we have our displacement is 0.284 miles. We know acceleration. That is 1.15 times 10 to the 4th. It'd be 11,500 if we weren't doing scientific notation. Miles per hour squared. And we want to know that we know it starts from rest. So what is our initial velocity if it starts from rest? All right, it's 0. And then we want to know what the final velocity is. So I like to put a question mark. Okay, so let's use equation 2. No time is involved in this problem, so we have the final velocity squared is equal to initial velocity squared, which is 0. I'm putting that there for illustrative purposes here. Plus 2 times the acceleration, 1.15 times 10 to the 4th miles per hour squared, times the displacement, 0.284 miles. Now, if you've forgotten how to put this scientific notation in your TI-84, I'll remind you. I'll just put it, hopefully you can see this, but we'd have 1.15 and hit the second and then the double E button, and then 4th. Don't put 10 to the 4th, just 4. That's 1.15. E means times 10 times 0.284. So that's 3,206. I forgot the times 2, sorry. I covered the times 2 with my calculator, but it's 2 times 1.15 times 10 to the 4 times 0.284. That's 6,532 miles squared per hour squared. And then we'll take the square root of that. And I think, personally, I think the fastest way to take the square root on these would just be hit the caret button, all right, and raise it to the 0.5 power. So it'll take your answer and raise it to the 0.5 power. That'd be 80.82 miles per hour. All right, pretty cool. So there's an example using equation number 2. All right, let's add one more to the mix. And these are some of the most famous equations in physics. The straight line motion equations. All right, equation 3. You got to memorize equation 3 as well. That is displacement is equal to initial velocity times time plus 1/2 times acceleration times time squared. The way we say that, V naught t plus 1/2 AT squared. Okay, let's take a look at on your own 2.3 on page 47. All right, it says a race car starts at rest, travels 1,321 feet in 11 seconds. What was the car's acceleration? Okay. So we know displacement is 1,321 feet. We know that time is 11 seconds. We know it starts from rest, so initial velocity is 0. So delta x is equal to v naught. Initial velocity is 0, right? So that makes that whole section 0. Right? So that's going to be 0 plus 1/2 times acceleration times 11 seconds squared. All right, and I forgot to put the 1321. So 1,321 feet. Sorry about that. You probably have to do some erasing real quick. Okay, so solving for acceleration, I'm going to pull that 11 squared underneath the 1321. And the 1/2 also, don't forget that. So in your calculator, well, let's just go ahead and, since we've had an entire summer off, what's the easy way to put that in your calculator? Well, I'd do 1321 divided by, left parenthesis, 0.5 times 11 squared, right parenthesis. And that'll make sure your order of operations is good. And that is 21.83 feet per second squared. All right. So that is a single example using all three equations, or one example per equation. For those three problems, you knew which equation you were going to use. But on the test, you won't know which equation to use. You'll have to figure it out from the problem. So let's work 3 more on your own problems, 2.4 through 2.6, where it doesn't really tell us which equation to use. We have to figure it out ourselves. So 2.4 on page 50. So all 3 problems are on page 50 to finish out this lecture. So 2.4 says if a car can accelerate from rest to a velocity of 60 miles an hour in 10 seconds, what is its acceleration? Okay. Well, we know our initial velocity, which is rest, is 0. We know our final velocity is 60 miles per hour. And we know that time is 10 seconds. We want to find out what's acceleration. Well, looking through these equations, if you have final velocity, initial velocity, and time, and you only need acceleration, the equation to use would be equation 1. However, I've got seconds and hours here, so I'm going to have to either change this to miles per second or change time to hours. I'm going to change time to hours. So we'd have 10 seconds over 1. We want to change that to hours, so put hours on top, seconds on bottom. The 1 goes by the bigger one, and there's 3,600 seconds in an hour. All right, so 10 divided by 3,600, 0.00278, don't round too much on these, hours. So now we have time with the same unit as velocity, okay? All right, so let's plug it in and solve for acceleration. So we have final velocity, 60 miles per hour, is equal to initial velocity, 0, plus acceleration, don't know that, times time, 0.00278 hours. All right, so acceleration is going to be 60 miles per hour divided by 0.00278 hours. All right, so 60 divided by 0.00278 is 21,583 miles per hour squared. All right, beautiful. Now, if you decide to work this by changing velocity into miles per second squared, you absolutely can do that if you want to try that. your answer will be 0.00167 miles per second squared. It's up to you if you want to try that or not. But I think the easier way to do this is to change time from seconds to hours. Okay, let's do 2.5. Voice just cracked, don't know why. I'm 56 years old. I probably should have stopped having my voice crack by now. All right, 2.5. Okay, so 2.5 says, in order to take off, a certain plane needs to start from rest and achieve a velocity of 150 miles an hour before it reaches the end of the runway. If the plane's acceleration is 20,000, 2 times 10 to the fourth is 20,000. You can leave it in scientific notation if you want to, but 20,000 miles per hour squared. What is the minimum length needed for a runway? All right, well, let's write down what we know. What do we know? We know that we start from rest, so V naught is 0. And we know we have a final velocity of 150 miles an hour. And we know our acceleration is 20,000 miles per hour squared. We want to know what's the minimum length needed for the runway. So that's displacement. Well, we don't have any time given, not in the problem, anywhere. So one equation of these three does involve time, and that's equation 2. So let's fill it in here. We've got 150 miles per hour. Don't forget to square it. Is equal to 0 squared. Initial velocity is 0. Plus 2 times 20,000 times delta x, which is what we're solving for. How long a runway, so that we don't run off the end of it. Okay, so delta x, we're going to just pull that 2 and that 20,000 underneath 150 squared. All right, so I'm just going to show you the calculator work here. Don't know if you can see that or not. Maybe you can zoom in if you can't, but it'd be 150 squared divided by, left parenthesis, 2 times 20,000, which you could probably do that in your head and just put 40,000. And that's 0.5625. Now it's displacement, a distance, so what would our unit be? All right, it's going to be miles, right? So a little over half a mile needed for this runway. Pretty short runway. All right, one more problem to go. I love these problems. They're really cool, I think. .6. All right, 2.6 says a biker can maintain a constant acceleration of 0.03 meters per second squared. If the biker starts from rest, how far can she travel if she keeps that acceleration up for 5 minutes? So I see we're going to have to make a conversion. We have minutes and we have seconds. It's pretty easy to change time into seconds. So time is, we got 5 minutes. We want to get that into seconds. Cancel out minutes. 60 seconds in a minute. The one goes by the bigger one, so that's going to be 300 seconds. So let's make sure to do that. The other things we know in this problem, we know acceleration is 0.03 meters per second squared. we know that the initial velocity starts from rest, so that's 0. Okay, we want to know delta x. How far? Not how long, but how far. So we're going to use equation 3. Now, I wish the author had kind of mixed it up to where we didn't go 1, 2, 3, but that's the way he went. But it doesn't necessarily go that way in the homework. Okay, so delta x, that's what we're solving for, equation 3, is equal to v naught t. So that's going to be, I'll just go ahead and show you, a 0 times 300 plus 1/2 times 0.03. It's a pretty messy 3, isn't it? Sorry about that. Times 300 seconds. I'm running out of space here. Don't forget to square that 300 seconds. So I'm going to write it again. 1/2 times 0.03 times 300 squared. Okay, so let's do that in the calculator real quick. 0.5 times 0.03 times 300 squared. 1,350 meters would be our displacement. All right, that is fun. Love those problems. So definitely got to memorize these 3 equations, but you will memorize them just by doing the homework. Okay, so what are the homework problems that go with this section? Well, we'll call this Chapter 2, Homework Number 1. We have review questions, page 69. The only one you can do is number 1. And practice problems, page 70. You can do numbers 1 through 5. Okay, so happy problem solving, and I will talk to you on the next video.